Hi, welcome to The Standard Model is Probably a Spherical Cow. Okay, so I'll start by defining those two terms. A spherical cow is an approximation that clearly doesn't correspond all that well to reality. And the Standard Model is our current best theory of particles and their interactions. In this video, the main idea that I'd like to cover is why it's reasonable to expect that the Standard Model will eventually be found to be a spherical cow. So first, I'll give a brief review of what spherical cow models are, and then I'll talk about why the Standard Model is, or at least is likely to be, a spherical cow approximation to some deeper theory. As we go, we'll also touch lightly on a few other things, like the methods physicists use to solve problems and the general progress of science. Toward the end of the video, we'll talk briefly about how some current experimentally observed deviations from the predictions of the Standard Model, like the discrepancy in G-2 of the Muon, fit into this picture of the SM as a spherical cow. Now, there are a few videos on this channel which are closely related and which you might want to check out. I'll only be briefly talking about what spherical cow approximations are, so you might want to also check out the video Spherical Cows. Another video that has a similar theme to this one is the video entitled Science as an Iterative Approximation to Nature. And lastly, there is another relevant video entitled Elon Musk said something important. Be less wrong over time. So I'd encourage you to check those out. Okay, so with that, let's ask, what's a spherical cow? A spherical cow approximation is an approximation that clearly neglects some important real-world effects. If we're trying to solve a problem involving a cow, approximating it as a sphere ignores a lot of details. So that's a spherical cow approximation. Now, one could ask the rather reasonable question, why would we ever want to use such an approximation? Well, sometimes a rough approximation is all we need. And also, sometimes a rough approximation can be the first step in building a better approximation. But here, I want to focus on one more situation in which spherical cow approximations can arise. So, let's say we have some scientific theory which explains some set of phenomena. And this theory has been experimentally tested under a range of conditions, and so far it seems to work. But then we do more tests. Under this new set of tests, we do at least one of the following two things. We expand the range of experimental conditions under which the theory is tested, or we test the theory with greater precision than what was done before. Now, let's imagine that under this new set of tests, the theory fails. Okay, so the initial set of experimental tests will be represented by this yellow circle. Under these tests, the theory worked great. But then we did this new set of tests, where this new set of tests are more precise than the old tests, or under new conditions not previously tested. And here, the theory failed. Okay, so the old theory failed, and we need to find a new one. So with much time and effort, we slowly build a new theory that is able to explain all of the experimental results obtained thus far. So, our new theory passes all of the tests both the initial set and the new set. Okay, so at this point we know that the old theory isn't exactly right, but that doesn't mean that we throw it away. If we later find that we need to make predictions for observations under conditions where the old theory approximates reality well, given our experimental precision, then it is still okay to use the old theory. While the new theory can explain all the experimental results that we've gotten so far, if we want to make predictions in the regime where the old theory works well, we still can. And we might want to do this if the old theory is simpler and easier to use than the new theory. In fact, the old theory can still be useful in situations where it isn't precise enough, if we know how to add corrections that take into account the most important effects coming from the deeper theory. So here we're using the old theory as a spherical cow approximation to the new theory. We know it's not exactly right, but it can be a good first approximation, and then we can add corrections to make that approximation better. So here I've represented cases like this by an additional blue circle. Here our old theory doesn't work great, but it doesn't fail completely either. This is the spherical cow regime. If we can add corrections to our spherical cow, it can be quite useful. Okay, so just to compare, we have our deeper theory, which explains all experimental results, and we have our spherical cow model. The deeper theory is our new theory, and the old theory has become our spherical cow. We would like to use the deeper theory, but it might be difficult and inconvenient to use. On the other hand, our spherical cow is easy to use, but isn't precise enough. So we can use our spherical cow, but with corrections. These corrections are added to the old theory to better approximate the new theory. This can be fairly easy to use and may be good enough for the purpose at hand. Let's look at an example in physics where this has happened. The relationship between special relativity and Newtonian mechanics. The predictions of Newtonian mechanics agree well with observation when all the speeds involved are small compared to the speed of light. But Newtonian mechanics breaks down when large speeds are involved. A deeper theory, special relativity, works when high or low speeds are involved. But if only low speeds are involved, the predictions of special relativity reduce to those of Newtonian mechanics. Let's illustrate this in a couple of different ways. First, let's imagine that we have some experiments that we can do to observe the differences between special relativity and Newtonian mechanics. And let's say our experiments have a fixed precision, but we can conduct them on systems where different speeds are involved. So let's illustrate schematically how Newtonian mechanics fares at low speeds, here represented as near v equals 0, and at high speeds close to the speed of light, c. If we conduct experiments where only low speeds are involved, Newtonian mechanics works great. But if we conduct experiments involving speeds near the speed of light c, Newtonian mechanics fails badly. In between, Newtonian mechanics can be an okay approximation. If necessary, we can include corrections to the equations of Newtonian mechanics which capture much of the behavior of special relativity. This last case is the spherical cow regime. Okay, now let's do something a bit different. Let's imagine that we do experiments with fixed speeds, but we do them with increasing precision. Again, let's schematically look at how Newtonian mechanics performs. If our experiments aren't so precise, Newtonian mechanics will approximate reality pretty well. If we do very, very precise experiments, we'll see that the predictions of Newtonian mechanics don't match reality. So, Newtonian mechanics fails badly. In between, again, Newtonian mechanics can be an okay approximation, and we can add relativistic corrections. So this is another way that we end up in the spherical cow regime. Newtonian mechanics can function as a very good approximation, or as a spherical cow approximation, to special relativity, depending on the specific experimental conditions. This is why we still use Newtonian mechanics, even though we know it isn't exact. So, in the progression of science, today's state-of-the-art theory is tomorrow's spherical cow. Right now, in particle physics, we have the Standard Model. The Standard Model correctly predicts a wide range of experimental results to high precision. But it's reasonable to expect that a deeper theory exists, and that for low energies, this deeper theory reduces to the Standard Model. As we do experiments at higher energies and/or with greater precision, the SM will approximate reality less and less well. It will go from predicting results correctly with high precision to only predicting them approximately. This is when we reach the spherical cow stage, and eventually it will likely fail completely. So now we'll talk about why we might expect this to happen. And as we'll see, it's possible we're already seeing the first signs that the Standard Model suffers from bovine sphericity. In order to do this, let's talk a bit about the Standard Model. Okay, here's the particle content of the Standard Model. It contains quarks and leptons. And it contains the gauge bosons, which transmit forces. It also contains the Higgs boson, although we won't be talking about that here. Let's look at those gauge bosons. The photon, represented by the Greek letter gamma, mediates the electromagnetic force. The Z and W bosons transmit the weak force, and the gluons transmit the strong force. So let's ask a question. Why is the weak force weak? To answer this, let's add the masses of these bosons to our table. The photon and the gluons are both massless. The carriers of the weak force, however, the W and Z, have masses around 80 or 90 GeV over c squared. The weak force was first observed in experiments where the energies involved were much less than 80 GeV. The observable effects of a given particle are small if the energies of the experiments are much less than the particle's rest energy, which is its mass times c squared. The weak force was first observed at energies much less than 80 or 91 GeV. Thus, its effects were small and the force looked weak. But if we do experiments at energies of around 80 GeV, the weak force isn't so weak anymore. At these energies, the effects of the weak force are important. So the takeaway of that is the following. At low energies, much less than 80 or 90 GeV, the effects of the weak force can be seen, but they are much smaller than those of the electromagnetic and strong force, which are both mediated by massless bosons. But at higher energies, this suppression for the W and Z masses goes away, and the weak force becomes important. With that, we are now ready to talk about why the standard model will probably be found to be a spherical cow. So, let's assume that the true theory of nature is something beyond the standard model. We will represent the true theory by this cow. Let's assume that in this theory, there are more particles yet to be discovered. A straightforward reason why they haven't been discovered yet is that they are heavy compared to the energies of experiments that we've done to date. So, in analogy with the weak force, there are a couple of things that we can expect. If we do experiments at energies comparable to the masses of the new particles, we would expect their observable effects to become large. But at lower energies, their observable effects would be small. So, at low energies, the deeper theory reduces to the standard model, like special relativity reduces to Newtonian mechanics at low speeds. But this means that the standard model can, at least in some situations, be used as a spherical cow approximation to the deeper theory. And the effects of the deeper theory can give small corrections to this spherical cow approximation. We don't know the deeper theory, but these small corrections might show up as discrepancies between experimental results and our spherical cow standard model prediction. Again, let's look at this schematically. Here we'll look at how the standard model will fare when tested at experiments of different energies. Here, low energy means energies tested up until now, and high energy means energies comparable to the rest energies of the new particles. At low energies, the standard model works great. But at high energies, the standard model fails badly. In between, we may see experimental hints of the deeper theory, which show up as deviations from the standard model predictions. This is why we build colliders of increasing energy. We can also look at low energy processes, but study them with increasing precision. So, again, schematically, at low precision, the standard model works great. At high precision, it will fail badly. And in between, we may see experimental hints of the deeper theory. So, this means we can look at low energy observables, but look for tiny deviations from the standard model predictions. In fact, there are a bunch of these low energy observables that are showing interesting deviations from the standard model predictions. If you'd like more info, check out the Miniseries on G-2 of the Muon, and also the video All Those Flavor Anomalies. So, to close, we have our standard model prediction and these tiny discrepancies that are showing up in Muon G-2, RK, RK star, etc., might be the first signs that we have to start putting legs and horns on this spherical cow.